Your smartphone has billions of transistors. Your computer can perform billions of calculations every second. And yet, most CPUs still run at around 2 to 5 gigahertz. Here's the weird part. In the early 2400s, computer speeds were increasing every year. 1 gigahertz, 2 gigahertz, 3 gigahertz. Many experts believed we'd eventually reach 10 gigahertz, 20 gigahertz, maybe even 100 gigahertz. But then something strange happened. CPU speeds almost stopped increasing. Today, even the most advanced processors on Earth are nowhere near 100 gigahertz. So what happened? Did engineers run out of ideas? Or did computers hit an invisible wall? To find the answer, we need to zoom inside a processor. Way inside. For decades, faster computers meant one thing: more gigahertz. Companies competed aggressively. Every new generation promised higher clock speeds. And it worked. A higher clock speed meant more operations every second. Consumers loved it. Manufacturers loved it. Everyone assumed the trend would continue forever. But then, around the mid-2000s, progress suddenly slowed down. The gigahertz race was over. And nobody outside the industry understood why. Let's zoom deeper. Inside your CPU are billions of tiny electronic switches called transistors. Microscopic machines, so small that millions can fit inside an area smaller than your fingernail. Every calculation your computer performs depends on these switches turning on and off. At first glance, the solution seems obvious. Want a faster CPU? Just switch them faster. Simple. Except it isn't. Because transistors don't switch instantly. Every transistor behaves a little like a tiny bucket. Before it can change state, it must be charged or discharged. That process takes time. Not seconds, not milliseconds, picoseconds. Trillionths of a second. Tiny. But when you're trying to perform billions of operations every second, those tiny delays suddenly matter. Yet surprisingly, this isn't the biggest problem. The real problem is even stranger. Imagine standing in one corner of a football stadium. You start a wave. People nearby react instantly, but people on the opposite side react slightly later. Information takes time to travel. Now shrink that stadium into a CPU. Inside a modern processor, billions of transistors must communicate through microscopic metal wires. And despite what many people think, electricity isn't instantaneous. Signals travel incredibly fast, but not infinitely fast. As CPUs became larger and more complex, engineers discovered something shocking. Sometimes the signal itself became the bottleneck. Not the transistor, the wire. A signal might need to travel across parts of the chip before the next clock cycle arrives. Increase the clock speed too much, and parts of the processor begin falling out of sync. Suddenly, a problem that sounds impossible becomes very real. Your computer becomes too fast for its own internal communication. But even that wasn't the final wall. There was something worse. Heat. Every time a transistor switches, it consumes energy. Now remember, modern CPUs contain billions of transistors, and they switch billions of times every second. At 2.4 gigahertz, the clock ticks 2.4 billion times per second. That means one clock cycle lasts only about 0.42 nanoseconds. Less than a billionth of a second. Now imagine pushing that same chip toward 100 gigahertz. The available time shrinks dramatically. The processor must work faster. Signals must travel faster. Transistors must switch faster. And power consumption explodes. The result? Heat. Lots of it. Enough to destroy performance, enough to damage hardware, enough to make the entire design impractical. Engineers weren't just fighting a speed problem. They were fighting physics itself. This is where the story takes an unexpected turn. Instead of making CPUs run faster, engineers changed the rules. Rather than one super-fast core, they built multiple cores. Rather than increasing frequency endlessly, they improved efficiency. Better architecture, smarter cache systems, parallel processing, AI accelerators, specialized hardware. This is why a modern processor running at 4 GHz can absolutely destroy an older processor running at the same speed. The number isn't the whole story anymore. And that's why gigahertz stopped being the most important metric. So, is 100 GHz impossible? Not necessarily. Researchers are exploring entirely new technologies: optical computing, 3D stacked chips, advanced materials, quantum computing. Future breakthroughs may eventually push beyond today's limits. But with traditional silicon processors, the challenge isn't engineering, it's physics. And physics doesn't negotiate. The next time you see a CPU running at 2.4 GHz, remember what that number really means: billions of transistors, billions of signals, billions of perfectly timed operations happening every second. The reason your processor isn't running at 100 GHz isn't because engineers failed. It's because modern computers are already operating astonishingly close to the limits of reality itself. And that's what makes them so incredible. If you enjoyed this deep dive into the hidden world inside your computer, subscribe to TechSphere for more technology explained videos.